This is a group literature review by Durga Prakash, Pranamurthy, and Sailesh. Computer graphics commonly refers to CAD, virtual reality, and physical simulation for fast collision detection. In comparison to computational algorithms that assume general position in real world degeneracies such as coplanar or parallel phases, so general position assumption would not work. Application delimits algorithm that can be used for instance via path taken is not prior. Hence, specified trajectories have to be checked. Similar instance of exact reproduction of mechanical process limits it. In this paper, we will see collision detection approaches and dive into the static inference tests and approaches and strategies we can implement to test those instances. Space-adaptive intersection is basic representation through extrusion method and constructive solid geometry representation. The extruded swept volume takes into account time implicit if the volumes interfere and the collision is detected. But in cases where no collision is happening, the extruded volumes do not interfere. Swept volume interference. The sweep function happens relative motion and one object with respect to another, considering one object is fixed and the swept volume by the other as a relative motion. This generation is computationally expensive. Simply, this restricts the shape and trajectories. The BF description of a polyhedral consists boundary primitives with their topological adjacencies. Multiple interference tests in this scenario. The closest points and the joint line of the two are computed and then the projections of the objects onto the meet at an instant, which is considered as the next time sample. At this specific instant, the newly considered closest points are computed. The positions where the polygons do not collide is considered too. Multiple detection approach. In the interference, it makes it susceptible to colliding first. Trajectory parameterization. The P and P prime are the initial and final positions of the PIs to find the triangle. If 0 less than or equal to t less than or equal to 1 and v is greater than or equal to 0 and the sum of u plus v is greater than or less than or equal to 1, it makes the point intersect the triangle. During time step, limitations on detecting and deformable models is minimization problem and collision detection can be easily derived for triangulated surface representation, similar for non-rigid surfaces. In convex polyhedral, we require three parameters associated which are required as variables. Linear inequality is attached to each vertex. The complexity of the intersection O log n, O log m, and a hierarchical representation of two polyhedral with n and m vertices. In each level, the original vertices are removed and then the edge and face are updated. Computing the minimum distance having no separation covers null space. Polyhedral with convex face includes the case of one polyhedron inside another. A face-to-face contact with vertex of another referred to as type A contact, and then edge with respect to another as type B. To predict the contact, taking into account of the matrix of face and the normal vector is considered true when it's greater than 0. In case of one inside another, drawing arbitrary A for the first if it intersects an odd number of faces, then inclusion exists. In general, polyhedron scenario, decomposition and convex paths method as a pre-parsing, but it is a trade-off between the complexity and the execution and resulting decomposition. Depends on which the algorithm can be used due to limitations on the availability of a solid decomposition or a surface decomposition algorithm will be present. In a direct approach scenario of a non-convex, a simple method of its edges intersects a face, we can conclude it. It intersection an edge in face by casting a ray from the point to check how many rays intersect. If its odd intersections does exist, to reduce complexity of this one vertex of the face or coplanar with the edges, which can determine if it's not. Hence concluding that methods by vertex location coordinates are required for computation as some determinants. Distance computation for collision time bounding. In spherical representation, due to elementary distance calculation between two spheres is trivial, describing objects as spherical cones and spherical planes. Viewing the scenario as collection of spheres, and hence the distance is a combination of the distances between two spherical cones and between a sphere and spherical plane. Complexities arise in implicit and parametric surfaces. Computing the closest to a three-form object and neglecting the points to satisfy condition in most distance computation algorithms. Specify features of a polyhedral are exploited and others can be used in spherical sets. The common approaches follow the two distinct streams, geometric and optimization. In bounding collision areas and objects in the common for one review in this paper, focusing on collision on relevant portions of the objects, one is to exploit the hierarchical of the volume bounding dependent on direct of motion by mentioning the forefront features of the temporal coherence is mentioned to keep track of the closest points. The advantage of hierarchical bounding is its ability to be used for both volume and boundary, where the others two can be suited only for boundary representation. In this, we consider collision detection problem in a 3D solid object moving amongst polyhedral obstacles. The object has 3 degrees of freedom and orientation is specified in all angles. In the other, the reference interference detection between polyhedral is the major context and the procedure to divide to avoid to have perform elementary tests enables. In the third, an efficient robust algorithm for finding points between time-dependent parametric and implicit surfaces. This algorithm detects simultaneous collision and multiple points of contact. In one, the problem is tackled radically different way trajectory connecting two arbitrary configurations for a moving polyhedron in a polyhedral environment is designed so that the obtained polynomial are of 3 degree of freedom that is lowest possible degree when the moving polyhedron. A polyhedral interference test is expressed as a combination of parameterized basic contact functions, these functions reflecting the spatial relations between the primitives of the PRAP of the polyhedron. The zeros of these functions delimit several time intervals whose combination according to the interference test provides the desired set of intervals over which objects would be intersecting if they were adhering to the predefined trajectories, while one uses parameterization based quaternions that other two allow the same approach using homogeneous coordinates. Collision detection, as you can see here, object starts at CI, moves along the straight line path in a configuration of CF in the B image, and the collision points along the path. In a generalized type A, the both A and B are moving and are constraints in the same form. In B, for the edge and edge intersection for the stationary B, as we can see here in the phase pairing and the edge pairing to perform interference detection between two boundaries of the polyhedron basis is applied to all possible edge and phase pairing. There exist two different types of contact. In contact AA for a given relative orientation between two polyhedron is for the vertex of one and the face of another. For type B contact, the relative orientation between two polyhedral of the contact edge of one and the edge of another. In order to refine the intervals and towards the solutions of the collision constraint, methods of computing are discovered using quasi-Moore form and interval inverse and matrix iteration in the interval linear equation solution algorithm. This computes the interval Newton step. Under the termination criteria, the two theorems, as you can see, the bounding sphere collision time, bounding in the image, the surfaces contact instantaneously on a curve, high dimensional region, both the surfaces contact at an infinite set of points through an interval of time. In this, we have described three basic types of interaction between polyhedral objects and the obstacles derived in the equation for each type of interaction. If the path of an object is described by the polynomials in the same parameter, and similarly object-obstacle constraints were then generalized for two moving objects, outline collision detection for a pair of uniformly moving objects as well. As you can see in the experimental results show a linear relation between the number of elementary edge phase tests that have to be performed and the total number of edge. The constant of linearity is close to 1. The representation captures the applicability features of these two polyhedron, which we have discussed as the SFOG in cases. A robust algorithm in this is presented handles a greater range of situations methods including solving transiency constraint and the constraint minimization algorithm, and the interval linear equation approach to interval Newton iteration are discussed in this. With respect to research question, like in the first, the general polynomial path or with different sets of algebraic constraints, are they possible to research in a segment? With respect to the second, the non-convex cases can be the same representation to be used to divide the rotational motion into intervals so that the constraints can remain constant. Sorting by lower bound of the objective function rather than by upper bound for isolated point collision case scenarios, can that be discovered? So our elementary pipeline is described. Starts from a detection to identification considering all internal and external factors. In the pre-collision phase, the primary goal is collision avoidance and anticipating the motion to miss minuses the impact effects. Major algorithms such as APF, elastic strips, and other variants of the above mentioned. Limitations in the field of speed of human motion is impossible to guarantee a collision-free behavior. In the collision detection phase, the binary output denotes if or not a collision is present. An intuitive approach is measured in electrical drives looking for far transient possible cause by collision. A mechanical limitation based on model control law is inherited to controller, but it is not possible to have a highly varying dynamic environment that reliably detect. In collision isolation exploited in manipulative scenarios, it is aims at localizing the contact point out of the n-body of what computation based on nominal desired trajectories. A common drawback in the fact of collision on a link propagated to the other links present. In collision identification phase, the idea is to view collisions as faulty behaviors of the robot actuating systems to design the detector taking advantage of the decoupling property. In collision phase, the information from the previous phases are classified as accidental or intentional and the severity level as time course. In collision reaction phase, to define better reaction strategies on them in all blocking the human reactions methodologies such as stop, slow, reflex control, impedance, and task relaxation can be used. In post-collision phase, it is enable autonomy on the decision of the robot as to make post-collision. It is not purely control-based implications such as artificial intelligence are commonly used.
In this slide, we can see the monitoring methods and the computational effort alongside the measurement quantities that are the advantages and disadvantages of the applicable methods to enable better choosing. As you can see in this chart, the collision monitoring methods for robots with flexible joints, performance of the link momentum observer, estimation of collision joint torque, and the largest possible. In joint monitoring methods can be dynamic or algebraic estimation of the associated with external joint torque via energy observer along with monitoring the tau external via inverse dynamics and estimating the tau x via joint velocity observer as discussed. In table of the three known industrial schemes, namely monitoring the absolute torque and the torque change and the torque tube. The first two methods based on absolute torque and on torque change simply check the motor torques and respectively their derivatives against threshold values. These schemes are very simple to implement and minimal computational cost. However, they have low detection sensitivity and are purely heuristic. Obviously, no isolation identification are possible. The energy observer, being quite simple on the other hand, is not able to detect collisions in specific directions or when the robot is at rest. On the other hand, two monitoring schemes based on velocity and momentum observations emerge for the following major advantages. One, as a simultaneous collision detection, isolation, and identification, and second, as a complete impedance form to reference trajectory and control law in execution. The best method to solve the context independent phases for the collision phase pipeline for both rigid and flexible robots. Experimental evaluations have been discussed in each section. In this scenario on the right, V external joint torque estimation in all 7 joint sinusoidal motion for tau x is under all ideal conditions of t greater than 1 and less than 4. In the first image of the plot, we can see the external joint torque and its estimation mu3 for the velocity observer and the momentum observer at the top directional initial configurations of the robot. In collision detection zone, as you can see the four phases in phase A, the external force is recognized by detection scheme and minimal delay. In B, no external force is applied and is at rest. And C, we see the detection is not possible, and in D, the robot is moving again but leads to an increase in sensitivity and monitoring signal. Research question. Conclusion and research question. The collision pipeline is defined as a systematic approach to comparison of all schemes in their use during collision detection, isolation, and identification. What could be the research question in this paper? In collision detection with link momentum observer being the best output scheme, can the same be implemented for rigid body? In algorithms for collision-free navigation, major research area has been primarily focused stationary objects and the global approaches. In moving obstacle and multiple vehicle scenarios are reviewed in this paper in reference to the global approach based on environments reactive methods based on sensory data and special focus on proposed navigation laws based on model predictive control and sliding mode control provided in this paper. In this section, a problem considerations outlining the real-world factors and the influence they can on navigation systems are explored. In the environment, there are multiple scenarios that can exist that are cluttered with multiple objects or static environment. Hence, a vehicle is spatially modeled as either a point or a polygon for all approaches. Polygons have supreme as they are commonly used to tightly maneuvering around closely packed obstacles. In the section of vehicle kinematics, many unique vehicle robots can be considered. Hence, holonomic unicycle and bicycle are introduced. Holonomic kinematic drives vehicle they have control capability in any direction. Unicycle are associated with particular angular orientation which determines the direction of velocity vector. Bicycle kinematics are described the car-like robots which are considered steerable front wheel separated from a fixed rear wheel. Commonly, vehicles with bicycle kinematics will be subject to an absolute bounce on their path curvature. In this section of sensory data, it can be defined as an abstract ray-based minimum distance tangent sensors and optical force sensors. Respect to the optimality criteria are methods of preferentially choosing one possible trajectory over another. A combination of the following measures are commonly used. Minimum distance is used, forming two configurations without obstacles as have a complex effect on the optimal path present and acceleration constraints are not present in this. Minimum wheel rotation of a differential wheel robots, minimum time and minimum control effort, and optimal surveillance rate are other common methodologies under them. This we can see a summary of traits characterizing methods as we have discussed in the reference. Model predictive control is an obstacle avoidance trajectory plan offline. There is a lack of flexibility is subjected to a bound disturbance. MPC combines path planning with online stability and convergence guarantees as it is done by performing the path planning process every time instant and applying initial control related to the chosen trajectory. Robust MPC lies within robust variants and are able to account for set bounded disturbances. Major categories include min-max MPC, where the optimization is performed with respect to all possible evolutions of the disturbance. In constraint-treating MPC, the state constraints are dilated and given by a margin so the trajectory can be guaranteed even in scenarios caused by the disturbance constraints by the obstacles. It is found based on minimizing of the cost function, compromising the control effect, and maneuver time. In Tube MPC, it uses an independent reference model of the system to ensure the actual state converges to nominal state. It does not take advantage of favorable distance, hence the benefits of navigation on linear model is used to making it use for robust linear nonlinear problems. Nonlinear MPC or approaches to MPC based navigation rely on linear kinematics model. A nonlinear trajectory tracking system can be used to ensure the actual state converges to nominal state. In scenarios of focusing more on control, MPC yields positive results and guarantees that safety are easier with kinematic models. Planning algorithms for global path planning, MPC can be used alongside multiple methods as well as completeness. Rapidly exploring random trees, common graph search algorithms such as A-star, D-star, which give us square Voronoi graphs. Optimization of predefined paths are methods which consist of Bezier curves, splines, and polynomial-based functions as they promise completeness, but are harder to implement in some situations. Others include MILP, a mathematical programming and optimization which use mixed integer linear programming constraint to model obstacles as multiple convex polygons. Tangent graph place planning and partially absorber Markov decision process are other common aspects which can be used as well. Sensor-based techniques for navigation commonly employed local knowledge. Global sensor-based planners use sensory information to build a comprehensive model. In local path planner, on both sensors to locally observe the nearest fraction of an unknown environment is used. Obstacle avoidance-based boundary following, unlike common algorithms to avoid obstacle, a boundary condition is held and stays still satisfied. A boundary following is a self-contained navigation of immediate interest. Distance-based approaches is work based on achieving the minimum distance to the obstacle. This distance is used as an input for guiding non-holonomic vehicles. A common limitation is that the vehicle must have constant speed. Introducing simple heuristics, we can solve this. Sliding motor control is known for the robustness against system uncertainties and good dynamics response and simple implementation. Common kinematic representation is classically described by the velocity and directional cosine or sine functions. The ability to alter the dynamics of the nonlinear systems and apply a discontinuous control signal forces the system to slide cross-section. The sliding mode control scheme majorly involves an hyperplane manifold which produces the system trajectory based on desirable behavior, and the feedback gains are found so that the system trajectory can have intersections and stay on the manifold. Bug algorithms are amongst the first target reaching methods. Most algorithms establish boundary following in close range as encountered obstacles. These algorithms do not include any prior sensory information. A reactive control law was established which made the bug type a target reaching for non-holonomic. Full information based is when information about the obstacles available. Wisbach class of algorithms are using abstract obstacle information navigates towards the visible edge of an obstacle inside the detection range. An MPC-based approach to boundary where it generates avoidance constraints and suitable target points to achieve boundary. Target planning using sensor information, a dynamic window, and curvature velocity methods are planning algorithms with a prediction horizon of a single time step. MPC type approaches are used to navigate vehicles and approach to collision using these methods estimate obstacle positions based on measurements combined with the state estimation method. APF computes the control input online based on available information, introducing unicycle kinematics, local minima avoidance, closed-loop performance, limited obstacle information, and actuator constraints are improvements that are commonly considered. In uncategorized approaches, a safe maneuvering zone based on kinematic unicycle model, the vector field histogram directs the vehicle towards sufficiently large gaps between detection rays. Probabilistic converge by use of deterministic tangent bug algorithms are considered in this section. In scenarios of moving obstacles, vehicle encounters, general planning works for dynamics, but the absence of obstacle assumptions is not possible to generate a viable path. Human-like obstacles, to avoid them, an approach based on concept of personal space is commonly used and works in scenarios. Known obstacles concept of velocity obstacle for more than complex vehicle kinematics, a nonlinear velocity obstacle in a 3D space can be extended. Path-based methods, arbitrary for trajectory planning to avoid collision, passive motion safety, is important to be able to move vehicle arbitrarily over an infinite horizon. Calculating the minimum paths for ensuring the robot lies in the set of points that cannot reach an obstacle. An assumption of non-empty set points is taken and allowing for avoidance over infinite horizon is present. Reactive methods, some common APF methods are extended in this, and sliding mode control techniques are referred as well. Multiple vehicle navigation, which includes communication, sensing, and dynamic constraints for collision avoidance problems. Communication types are modes of communication like direct state, which is based on sensor information to measure the state in a single direction, broadcasting additional variables like current trajectory is used for exclusion-based path constraints. Two-way communication is getting decentralized optimization algorithms, commonly decentralized MPC, and its variants are discovered in detail. Reactive methods are viewed in two major categories: a potential field method, which is constructed to repel other vehicles, exists for velocity control uni or linear vehicles, along with static and dynamic environment scenarios. Reciprocal collision avoidance achieves collision by assuming each vehicle for a pairwise conflict based on implicit cooperation. A method like distributive reaction collision avoidance is discussed, which ensures minimum speed constraints are met on a global level. Decentralized MPC finds near optimal solutions for multi-agents and multiplex MPC with a robust control input or an acknowledgement of signal before implementing trajectories or other approaches. Even single communication has been viewed in this section. Problem description method. A robust distributed preceding horizon control (RDRHC) is approach for simultaneous tracking, regulation, and formation of multiple perturbated vehicle collision avoidance. Stochastic optimal control for nonlinear constraint trajectory optimization are discovered. Novel approach to deal with chance constraint navigation is discovered in this. Here, the state constraints are dilated by given margins so that a trajectory can be guaranteed to found even when disturbance causes the state to evolve towards the constraint imposed by obstacles. As we see, it is common in all three. The basic argument shows existence of a future viable trajectory by using a feedback term through a feedback input it not directly used for updating the trajectory. This is commonly used for vehicle navigation problems. For example, a system has been described where an obstacle avoiding trajectory is found based on minimization of cost function, compromising the control effort and maneuver. In this case, convergence to the target and the ability to overcome bounded disturbance can be seen. Because algorithm 2 is an adaptation of algorithm 1 by substituting the optimal solution with feasible trajectories constructed the recursive feasibility of optimal control, robust admissibility of desired constraints, collision avoidance between multiple vehicles, and robust convergence of tracking and formation can be guaranteed by applying either algorithm 1 or algorithm 2. If they are guaranteed by trajectories constructed for the graphs of orientation, linear speed, angular trajectories from them, we can say the deviation evolved and solved the nominal trajectories which are larger than the feasible trajectories, making it more freedom by the online optimization present in the algorithm. The tube stochastic optimal control by uncentered transform introduced as a first step change it from stochastic to deterministic, and the objective function is defined because of the linearity of the value operator. In the case of a double integrated problem, which is discussed, the following parameter were used, which produces the nominal trajectory and the control inputs. A Monte Carlo situation is run, which control profiles are viewed. The MILP and the LP were solved on the sections, and proposed approach and cluttered map can be viewed in the next slide. And the comparison in computation can be seen in a more cluttered environment than the previous one. The approach is also tested in a delta t of 0.01 and given steps of which is set as 30. As we can see, this is the simulation that results that we have had, and as we've talked about different algorithms that were approached for the bottom four, and conclusion and research questions that can be asked with respect to this. Can a real-time application use have online optimization present along with the algorithm? Can this can produce a high fidelity uncertainty quantification method and improve the accuracy of the uncertainty propagation in a non-Gaussian manner? Can a low complex and economic encoding of the problem be viewed and reduce the number of binary values for computational effort? Conclusion. A synchronous robust distributed RHC algorithm is presented for implementation which can be recursively applied to achieve the desired control objectives. Furthermore, the presented algorithm is adapted by avoiding online optimization to meet requirements of a real-time application. The method approximates the stochastic process as a Gaussian process and employs the uncentered transform to make a stochastic optimal control problem a deterministic problem. The two numerical examples illustrate the robustness and the optimality of the proposed method. This paper proposed three enhancements: a chance constraint MPC, navigation formulation, namely an improved binary variables encoding for obstacle avoidance, a piecewise linear approximation of the inverse error function, and a variable horizon formulation. The ability to predict what motion a robot will take based on aspects, we need to measure the effects they have on humans. In this paper, major work has been done to examine the human response to motion level robot adaptation to determine the effect on team fluency, human satisfaction, and perceived safety and comfort. Efficiency tests and situational awareness, comfort, and safety are primary to be favorable for a collaborative environment. The objective of this paper is to aim and understand how to work more closely in an environment together and develop a system on create a collaborative environment. This figure we can see a shared workspace in which human and robot are placing screws, and the other simulation depicts the shorter path as dash narrow and human aware motion as a solid. Given an expected human workspace represented as a cylinder, in this experiment the task is to describe by placing 8 screws in defined areas, and this process from initial actuation and final screw worked on an average of 52 seconds. As you can see in this diagram, which depicts the experimental procedure in the chart, the left section represents the human-aware first conditions, whereas the group on the right is a standard first condition. A repeated measure design was done with randomly selected groups. Moving on to the results, the quantitative team fluency metrics, as you can see in the mean values with error bars for which indicated each division task execution percentage of concurrent motion. Average separation distance between human robot idle time, human idle time for both standard and human aware robot executions on a subjective evaluation scale after both conditions for both set of people was done based on human or standard, given the minimal demonstration of the robot's ability to avoid conflicts, had varying results in that front. Limitations and conclusion. The result presented had various differences which can be caused by multiple reasons, such as the differences in team fluency for collaborative environment and the differences in human satisfaction and perceived concept of safety and comfort from them, and the shortcomings caused by human and robot idle time and the learning differences that can exist from the randomly formed group. In this paper, an adaptive motion planning technique was followed, and the results indicated people learned to take advantage of human aware motion even when performing novel tasks with limited training. This leads to a higher degree of perceived safety, which reduces the potential for stress-related health problems and improves the fluency in team perspective. These are references for the paper that we have discussed. This is just the continuation of the references that we have done.